Hey Wheaton North, Mr. Yergler here. We've done Lewis dot structures with individual atoms and with single bonds, but we also need to do it with double and triple bonds. So I'm going to show you how to do that. Let's get started. If you don't have a simple method of doing these Lewis dot structures, if you couldn't summarize it, I want you to write these steps down, especially if you're not completely sure on how to do Lewis dot structures. This step-by-step process is really the easiest, most straightforward way that I know of for doing Lewis dot structures, especially complicated ones like multiple bonds, like double and triple bonds. Okay, so pause the video and write down these steps. We'll be using these when we do some examples. All right, so we need to first talk about what is a double and triple bond. We know in a single bond, we talked about this yesterday in the notes 1, a single bond is a shared pair, and a pair, remember, is 2 electrons, right? So we're sharing 2 electrons, one from this atom and one from this atom. And this is 2 atoms where you have a single electron off to the side, right? It's not paired up, so it can accept, so to speak, another electron from another atom. All right, so they share electrons. What they're really doing is they're fighting over them, but we say that they're sharing them. Now, sometimes the atoms will actually physically get a little bit closer to each other, and they overlap more of their electron cloud, and so they share more than just those 2 electrons. And they always share them in pairs. So they can share 1 pair here, or they can share 2 pairs, which would be 4 electrons here. And a double bond is stronger than a single bond because you're sharing more. You're overlapping more of the atom, you're sharing more electrons. We can also have a triple bond, which is 6 shared pairs. That would be an example right here, where you have 1 pair of valence electrons on the outside. These 2 electrons here are inner electrons. They're not valence electrons, so they're not involved in the bonding at all, right? So we have 1 pair that's unshared when we're talking about valence electrons, and we have 3 shared pairs right here. Okay, let's do a few examples. One thing real quick: a triple bond is the strongest, which makes sense. What we're going to do is we're going to do a few examples, and I'm going to show you how to do the double bond, triple bond, how to identify if there's a double bond or triple bond. All right, you kind of want to just compare the number of single bonds that the central atom can form compared to the number of peripheral atoms, the outside atoms that are in the formula. For example, this carbon can make 4 bonds, right, because it has 4 open bonding sites or bonding domains. This atom, nitrogen, one of the sides of the atom, one of the domains, is already paired up. So it can actually only hold a maximum of 3 bonds, right, because there's only 3 places that it can accept more electrons. So we could say that nitrogen, theoretically, could form up to 3 bonds. It doesn't necessarily mean it's always going to be a triple bond, but it could go up to a triple bond. We'll actually do 2 of these examples. CH4 we're not going to do. We could do that later. Let's look at CO2 first. Okay, I'm going to switch to actually doing this on paper because I think it's a little easier for me to show you how to do it. Okay, let's start with carbon dioxide. So go ahead and write this out, CO2. And if we follow our steps, we need to first figure out how many total valence electrons there are going to be. So carbon would have 4, and oxygen would have 6, and there's 2 of them, right? There's 2 oxygens, so it's actually 6 times 2, so that'd be 12 plus the 4 would be a total of 16 electrons, right, that we have to work with. Okay, now you need to pick your central atom. Carbon is pretty much always going to be the central atom. In fact, I can't think of an example where you're not going to have carbon as a central atom if you have carbon. Okay, so arrange carbon with the center and the oxygens on the other side of it, and they could be up here and down here. That doesn't matter. Now the next step is to put a pair of electrons as a bonding pair in between those 2, in between the carbon and the oxygen. Okay. Now we have 16 electrons to work with. We've already used 4 of them. So the steps that we have say that we're going to start at the outside atoms and add electrons until we run out of electrons. So 2, 4, 6, 8, 10, 12, 14, 16, right? Now, I'm doing this in marker because it shows up a lot better on the screen, but you want to probably be doing this in pencil because we're going to have to make some changes here. We need to double check that all of our atoms have 8 electrons around them. They're filling the octet rule, right? Oxygen here has 8, right? And this oxygen has 8. However, if you look at carbon, it only has 2 pairs, which would be 4. It doesn't have enough electrons. But we can't add anymore because we're already at 16. So what we have to do is we actually have to take 2 of these and move them into a bonding pair. Okay, so we're going to cross those out. And what you really should do is do this in pencil. Okay, there, I just rewrote it with pencil, and I guess it shows up okay. I kind of have to make my dots a little bit larger than I normally would. So I've moved one pair here into a double bond, and this pair over here into another bond. I've spread out my electrons because they tend to repel each other, and so I'm going to just draw them off to the side a little bit instead of right below and right to the side, like that. Okay. Now this is your double bond right here. We're sharing 2 pairs of electrons, right? And so that's a double bond. Let's do another example. Let's do COCl2. First, figure out how many electrons we have. We have 4 with carbon, 6 with oxygen, and chlorine has 7, and there's 2 of them, so that's 14, right? Plus the 10 over here, plus the 4 and the 6 would be a total of 24 electrons to work with. All right. Now my carbon is going to be my central atom. I'm going to have oxygens and 2 chlorines. It doesn't matter where we put them. I'm going to put one here and one here. Okay. Now, set up a shared pair of electrons in between for starters, and then we're going to fill in the rest of the electrons, starting with the outside atoms, and then if we have extras, we'll go to the carbon. Okay. So chlorines only have one bonding site open, right? Because they have 7, and so they can only form one bond. All right, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so I'm done adding electrons, but notice that my carbon only has 6, right? 3 pairs. So we're going to need a multiple bond here. Now we can't take it from chlorine. This is important. You might want to make a note of this. We can't take it from chlorine because remember, chlorine only forms one bond. Because if you were to draw chlorine by itself, it would look like this, where it only has one spot that it can bond, right? It can't form multiple bonds. So we have to take it from oxygen. So I'm going to take this one. I'm actually going to erase this and move it to right here. So now we have a double bond oxygen. We have 8 around this oxygen, and we now have 8 around the carbon, right? Which is exactly what we want. Let's do one more example. Nitrogen gas. First, start with the number of electrons. Nitrogen has 5, and there's 2 nitrogens here, so we have a total of 10 electrons total to work with, right? There isn't really a central atom here because we only have 2 atoms to begin with. So I'm going to set it up like that. We have 10 electrons to work with, so let's get started. 2, 2, 4, 6, 8, 10. Now you can see right away this nitrogen has 8, but this one only has 4. So what we're going to need to do is we're going to need to move a pair. I'm going to erase this pair. Doesn't matter which pair you erase. And move it to the bonding pair. Move it as a bonding pair. You're changing a lone pair to a bonding pair. Now let's check. This nitrogen still has 8, right? 2, 4, 6, 8. But this nitrogen has 2, 4, 6, only 6. We're going to need to move another pair. Okay. So I'm going to erase this pair and put them as a bonding pair in between. Okay, now let's check again. This nitrogen has 2, 4, 6, 8. Perfect. This nitrogen has 2, 4, 6, 8. Perfect, right? So we actually have a triple bond here between the 2 nitrogens, which is actually the example that we showed you earlier. Did you get all that? If you have any questions on this, if you're confused by any of it, make sure you write those questions down right now. That way, in class, when we go over it, you can ask those questions and get that cleared up, okay? Lewis dot structures, like a lot of things in chemistry, like a lot of things in life, requires a little bit of practice to get good at it. So if you don't feel like you're good at it now, that's kind of normal because we're just starting it for the first time. This is Mr. Yergler, signing out.